I'll share my experience building a reduced version of the IBLRig task. My experiment is to evoke visual responses in mouse cortex with coordinated perturbations to identify how thalamus shapes those responses. In my experimental structure, each trial is composed of an intertrial interval, a drifting grading presentation, and for interleaved stimuli, concurrent LED drive for opsin perturbation. The core of this structure is greatly reduced relative to the original task reported by the International Brain Lab in their eLife 2021 manuscript. Building this reduced version has helped me to orient myself in the inner workings of the IBLRig package and its interactions with Bpod, Bonsai, and Neuropixels. So I'm sharing my experience in the hopes that it helps you in your own task design. My setup's pretty much according to the IBL's appendices. I have two computers, one installed with the IBLRig wizard and Bonsai and affiliated packages, thus serving the coordinated production of visual stimuli and drive to my opsin. The other mainly serving the Neuropixels device monitored with Open Ephys, which will receive inputs from the IBL computer to coordinate. So most of this presentation will focus on synchronization between the Bpod components, that's the left side of the screen, because IBLRig, Bonsai, and Bpod are a huge chunk of software. I'll show you how I approached their structure. So let's get to the hub to look around the IBL code. On GitHub, we'll explore a few folders, starting in IBLRig tasks. This folder hosts the code behind the various tasks you'll find in the IBLRig wizard GUI when you launch it from command line. So here you can choose a task and find a file of code with the corresponding name in IBLRig tasks. So now we're feeling a bit more anchored, relating the GUI with some code. I recommend habituationChoiceWorld as a place to start, as its structure is quite minimal compared to the parent classes. This task is set up for habituation prior to training, so it's not mouse behavior oriented and thus has a simpler structure than, say, training phase or biasChoiceWorld. So let's take a look inside habituationChoiceWorld. Each task folder contains the task code, which in this case just calls on the class of the same name in the IBL file baseChoiceWorld, where we'll get in a moment. Each task also has a parameters file where you might set parameters to differ from the default settings called by baseChoiceWorld. So next we'll consider habituationChoiceWorld session, imported in that first line of the task code. And we'll find two files that parallel task and task parameters. These are baseChoiceWorld and baseChoiceWorld's parameters. Back up to IBLRig to find the next folder where that's defined, the IBLRig subfolder. So there's a lot of good stuff in here. I'll highlight the scripts I found the most useful. Let's go straight to baseChoiceWorld since that's where the task is imported from. After a bunch more importing, this code can really just be reduced to a bunch of classes. Here's the phylogeny of these classes, where the great matriarch is ChoiceWorld with two subclasses, habituationChoiceWorld and activeChoiceWorld, and the latter has its own pair of subclasses. The big trait that ChoiceWorld session and her descendants share is taking in a bunch of mixins. Mixins are used to modularize functionalities that may differ between subclasses. These mixins are essentially actions coordinated with the elements of the Bpod system, with Bonsai, etc., that are strung into sequences to build experiments. And remember, we're in habituationChoiceWorld. habituationChoiceWorld has a whole slew of definitions inherited from ChoiceWorld session, and 3 set to differ from the parent class. First is get state machine trial. I'm switching views here a little since I'm off GitHub now in my personal scripts. The state machine in question here being the Bpod get state machine trial sets the sequence of states making up each trial. habituationChoiceWorld session has its own definition of this function that overwrites the more complex parent classes. Look for the add state command, which assigns two qualities to a state, its state change conditions, which dictate the next state, and output actions, which generate actions. These can be TTL outputs or mixin mediated actions. Hence, these states are strung together, proceeding through an intertrial interval, stimuli presented at two locations, a reward, and a post-reward state. This is still more complicated than the task I want, so I modified it. First, I got rid of a lot of those states. When I tried to get rid of reward, deeper bugs emerged, so I managed this by bringing reward time down to 0, kind of a hack. This left only a few lingering challenges. First, how to interleave trials with LED perturbations, and second, how to vary stimulus qualities like contrast or orientation. For the problem of the LED, I gave my subclass a new input, OctoFlag, which is generated earlier in the code as just 0 or 1. Then, depending on the flag state, a given trial proceeds from the intra-trial interval to one of two versions of stimon, one that simply produces the grading, and the other additionally outputting a TTL via the Bpod's out2, through the output action specifying a BNC2 value of 255. So what of varying the visual stimuli? This brings us to the second definition, draw next trial info, where for each trial, the stimulus qualities are drawn from assigned parameters. These can be singular values or arrays of values to interleave. In my design, such arrays include contrast and stim angle. If you want to modify or add a new stimulus parameter, just do so in the parameters file. During the experiment, Bonsai Visual Stimulus Mixin sends these parameters to Bonsai via a protocol described in the base tasks. And it does this on a per trial basis to produce appropriate gradings. Bonsai itself gets pretty hairy, so let's take a quick look at the workflow for the file named among the parameters as Visual Stimulus. In HabituationChoiceWorld, this file is called gabor2d.bonsai, and you can find it in the IBL folder, Visual Stim. So let's open that in the Bonsai program to briefly examine its structure. At first glance, the Bonsai workflow looks simple, but this stim element is nested, and so are many objects in its workflow. So let's focus on two. Environment definition first sends the stimulus parameters set during DrawNext trial to Bonsai by the Bonsai visual stimulus mixin via a protocol described in the base tasks, and then combines these to produce drifting grading of the prescribed parameters. In save data, you can choose which settings to document and set their save path, where you can check later the output is matching the parameters you think you've set. As IBLRig moves through the defined states, it's producing many analog and digital signals that output to a terminal block. On my rig, a BNC2110. You can record all of these in Open Ephys, but if you're also collecting Neuropixel recordings, it will be important to sync these two data streams. They're on different clocks by default. But the IMEC base station has its own internal clock, and it can send a syncing signal to the BNC2110 to coordinate the two streams. Here's what that will look like in Open Ephys. Visualizing BNC2110 inputs with the NIDAC module, you should see an analog signal step corresponding to IBL events. My channels are a starter signal on one, and on two, a photodiode tracking the visual stimulus. You can also see digital events, which are imposed on the analog signals as these blocks of color. The trigger from the IMEC base station is one such digital signal, and the only one that should also appear imposed on the Neuropixels traces on the left. Theoretically, we could align these two continuous sources manually now, but better yet, let's get Neuropixels and the NIDAC running on the same clock. Use these channel monitors in the record node to make sure the Neuropixels channel is set as the master subprocessor. But if these channel monitors flash orange, don't proceed with your experiment. It indicates something is wrong with syncing. In my hands, it was a sync signal that was too frequent, so now I stick with the 1 Hz signal. The syncing takes a moment, so press play to initialize before you hit the record button. Post hoc, you can use your digital events or threshold detection of analog shifts to align neural spiking with all sorts of task events, for instance, by making event-triggered rasters to claim some causality. Voila! Catch you next time.